We've talked about limits of functions to two variables. Now we want to know if we can use that to get a version of a derivative for them as well. However, before we can do that, we need to know what our derivative would even mean. For a function of one variable, the derivative represents the slope of a tangent line. For a vector-valued function, the derivative represents the direction of the tangent line. However, let's look at the graph of a function of two variables. So let's start off with f of x, y, is equal to 5 minus to x squared over 9 and minus y squared over 4. So just go ahead and put that in here. I'm going to even name it as f of x, y. And we get this thing. This is actually the top part of a elliptical paraboloid. And I'm actually going to change the colors of this. It'll be a little easier to see what we're doing later on. Let's just do that. If we take a point on this paraboloid, I'm going to go ahead and take the point 3, 2, 3 because that's a nice point with integer values. It's this point here, this A. We want to know what exactly would be the equivalent of our tangent line at that point. In fact, it looks like there should be a lot of different tangent lines going in various directions. In fact, we should have an entire tangent plane to this surface. How are we going to capture all of that information? One idea might be that our derivative should tell us the slope in the steepest direction, though that would beg the question of how do we find which direction is steepest? We could kind of eyeball it maybe, but how do we mathematically determine what that direction really is? Maybe we'd like to just get a way to get the slope in any direction that we specify in the first place. Another idea would be in order to get a tangent plane, we might try to get a vector that's perpendicular to the surface in order to use that to get the equation, because that's how we got equations of planes back in chapter 12. We will eventually be able to do all of this, but we are going to start off doing something a little bit simpler that will turn out to be enough to actually get to all the other stuff. That we don't have to do all that stuff in generality. We can actually do the simpler thing and then use the results of this in order to solve those other problems. What we're going to do is we're going to take two specific directions that are easy to work with, specifically the ones that are parallel to the x and y directions. So let's take a plane that is parallel to one of our coordinate planes. Specifically, since we know our x and y values of our point, we're going to specifically be looking at this point here. Since the x value is 3 and the y value is 2, let's pick a plane that passes through this point where, let's just start off with y equals 2. This plane intersects our surface in a curve. There is a curve here. And in fact, GeoGebra is nice enough to allow us to select those two and find an intersection of them. It gives us a very nice curve, and it even gives us an equation of that curve, though given in terms of multiple functions, multiple equations. How might we figure out anything having to do with that curve? Well, you could say it's just a curve in a plane, and so we can actually just do a regular differentiation. So what did we do there? We specified that y is equal to 2. On that curve, y is always equal to 2. So we can just go ahead and replace the y that's in here with 2. We go ahead and plug that in here. We have 5 minus x squared over 9, and then 2 squared over 4 is just a 1. Or in other words, we're going to get 4 minus x squared over 9. we could view this as a function of just x. In fact, it looks like that's all it is. We could even just give it another name if we want to specify that we are just working with this as a function of x. The derivative of this function is pretty easy to find. That's just a Calc 1 problem, and it's not a very difficult one. The 4 goes away, we bring down the 2 and reduce our power by 1, get negative 2/9 times x. If we go ahead and use the value, so we're talking at the point 3, 2, 3, so our x value here was 3. We can go ahead and plug that into our derivative. So negative 2/9 times 3, which is negative 2/3. And that's going to give us a tangent line using this derivative of, well, maybe I won't write that out just because I don't want to get too confusing here. So this is a derivative, but when it's not in the xy plane. So I don't want to write something like y equals mx plus b because y and x are not really in there. Maybe we could do something like z equals something in terms of x, and just keep in mind that y equals 2 is in there. In fact, maybe that's what we'll do. Our slope here is negative 2/3. We'll go ahead and use the point slope form. So our point here, since we're working with x and z, are 3 and 3. So we have x minus 3 times negative 2/3, and z minus 3 is equal to that. I'll go ahead and actually move the minus 3 over here when we put this into our graph. So I'm going to go ahead and graph the line, which, because we are working in three-dimensional space, I'm going to write this as a curve, where my x value is going to be t, my y value is always going to be 2 here, and I'll use my formula for z, but I'll replace the x with our t. Obviously, the variable here is t, and I'll just pick some wide range. We get a line. A nice tangent line is tangent to the curve and to the surface as well. In fact, you could say it is the tangent line to the surface at that point that is parallel to our x-axis in a way. Not really, I guess parallel to the xz plane, if you want to be more specific. What about if we go the other direction? So here we fixed y. How about we fix x instead? If we set x equal to 3, now we get a different plane that's parallel to the yz plane this time, and it again intersects our surface in a curve. We go ahead and actually draw that curve in there. We get another curve that is, it's not actually perpendicular to our first curve because they do actually intersect in a different angle here. But if you look at them from above, they look perpendicular. Let's do all the same stuff that we did with our first curve for this other curve. So again, here we just let x equal to 3. That means we replace x by 3, but we leave y alone. Go ahead and plug those in here. Now 3 squared over 9 is a 1. We still have our y squared over 4. And that simplifies to a 4 minus y squared over 4. Of course, we could consider this a new function, a function of y, just y. And now we can do all the calculus that we want, our Calc 1 stuff, for this function h. H prime of y, again, pretty easy. That 4 goes away, we bring down the 2, and actually this time the 2 cancels out part of our 4, so we get negative y over 2. If we go ahead and plug in our value for y, remember our value for y is 2, then the derivative at that point would be negative 1. And we end up getting a formula. We could say z minus 3 is equal to this derivative, this slope, which is negative 1, times y minus the y value of 2. Actually, this one can simplify very nicely. Z is equal to negative y, but then plus 2 and plus 3. In fact, let's go ahead and put that 5 in front. Z equals 5 minus y. So you go ahead and put that line in here. Remember here, our x value is staying at 3, so we're just keeping 3 there. I'm going to say y equals t, and then I'm going to use my formula for z, but replace the y with a t. And again, quite a big range for our t value. So that's another tangent line to our surface, and this time it's parallel to the yz plane. And in fact, you can almost already tell that a lot of information about our tangent plane is already contained in here. The tangent plane is the only plane that actually contains both of those two lines. And that's kind of the trick to making all this work. That once we have these two derivatives, we actually know a lot about what the function is doing in a calculus sense at that point. We are going to call these kind of derivatives the partial derivatives of the function f. And note that in our definition that the book gives us, it writes the partial derivatives as limits, but these limits are really just keeping one of the variables as a constant value, basically ignoring one of the variables and only taking the derivative with respect to the other variable. So here, if you took out the y, this would just be the formula for the derivative of a function of just x. It's just kind of ignoring y and treating it as if it were just a constant. Just kind of like what we did in the previous example, where say we let y just equal 2, and then the 2 was a constant when we were differentiating with respect to x for our first part. And then the other way around, when we replace x with 3 for the second part, we just treated x as a constant. But here we're going to keep x and y in there so that we can get functions of two variables as our derivatives. So let's just see this in practice. Here we have a function of two variables, x and y, a fairly simple polynomial function. We're going to take as derivatives with respect to x and y, the partial derivatives of this function. Notice that we're using f sub x and f sub y as our notation for our derivatives. Essentially, this is our f prime notation, except if we were just to use f prime, we wouldn't be able to tell which one's which. So you can go ahead and write f sub x of x and y. Here we are treating y as a constant value. So you could go ahead and replace it. You could say something like x squared plus 5x times, I don't know, b to the third power, and treat b to the third power as just some constant thing. I'm going to keep writing them as just x and y. If this helps you, just be aware that you're going to have to get used to being able to work with x and y in the long run, because we're going to be doing this using these partial derivatives quite a bit. So this would be a crutch for now, but don't do this forever. So what is our partial derivative in the x direction? Well, we have x. We just do them the same way we normally would. Nothing about their definition changes all of our laws of differentiation. So we can break it up over the sum. We have x to the fourth. We differentiate that by our power rule. We have 4x cubed. Now we differentiate 5xy cubed. Keep in mind that here that 5y cubed is being treated as a constant. So we're just really differentiating a constant times x. The derivative of a constant times x is just the constant. So we're just going to be left with a 5y cubed as that part. our partial derivative with respect to y. We do it exactly the same kind of way. We can split it up over the sum. Derivative of x to the fourth. Well, keep in mind here, x to the fourth is a constant. What is the derivative of a constant? It's 0. So I'll go ahead and put the 0 there for now. But you could even leave that out. Derivative of 5xy cubed. 5x is now just a constant. So it just sticks around. We differentiate y cubed, which is 3y squared. 5x times 3 is going to be 15x. And we have that y squared. Or we can just go ahead and write this as 15xy squared. And those are our partial derivatives for any point on the surface, if we were to draw the surface corresponding to this function. Problem 28, this one looks a little bit more complicated at first, but keep in mind that when we're doing partial derivatives, we're never going to be treating x and y as variables at the same time. So in fact, this is going to be a lot simpler than it looks. When we differentiate in the x direction, we do f sub x. Here, y is being treated as a constant. So we have x to some constant power. We just have a power function. And we can use the regular power rule. That means we reduce our power by 1 and pull the power out in front. So we end up with a y out in front. We have an x to the y minus 1. Or we could even write this as x to the y minus 1 times y if you prefer to have the x in front and the y in back. But there's really nothing else to it. Y here is just a constant. It's no different than if we had x to the n and we were pulling the n out and subtracting 1 from the n in the exponent. What about f sub y? Well, this time, x is being treated as a constant. So this is a constant value to the y power. That's an exponential function where the base is equal to x. Think of it as e to the x, except our variable is y instead of x, and we're using something other than e for the base. And recall that we had a formula for differentiating such a function. Remember, e to the x, when you differentiate, you just get e to the x. Any exponential function is going to be similar, where you end up getting to keep that exponential, but if you have a base other than e, you end up with an extra natural logarithm of the base being multiplied in there. If the base is equal to e, ln of e is just 1. So it's just kind of there, but you don't have to see it. So fairly complicated, but because we're only working with one variable at a time, it's not really that bad. There are actually a lot of different notations for partial derivatives. We're basically going to be sticking with the f sub x and f sub y notations. You can actually leave off the function part of it. Just write that as f sub x and f sub y. That, like I said before, that's basically our f prime notation that we like to use in Calc 1 and 2. Just now we have to specify which variable we're using at any given time. There's also these curly d notations. Basically, we read this as just df dx or df dy. That's just the same as doing something like df dx without the curly d. I'm not entirely sure why the past mathematicians decided we couldn't just continue to use just normal d's in there, but it has become quite standard to use curly d's whenever we're working with partial derivatives. In fact, a lot of people will actually, when they're actually doing anything that could be partial derivatives versus normal derivatives, or basically Calc 1 derivatives versus Calc 3 derivatives, they'll actually switch between them in the same problem. I find it a little bit more of a hassle than I'd prefer, but that is the standard to do it that way. So I'm going to stick with that whenever I do actually use the curly d notation, and you should expect to see that when you're actually working with this out in whatever field you might be working in. I will mostly only use the curly D notation when we're actually doing something like this. When we have to maybe use the dxdy, or sorry, the ddx and the ddy notations in the middle of a computation, like something like I have a function of two variables, say 2xy. I want to differentiate with respect to x, and I don't want to come up with a function name for it. I just want to write down the formula that the derivative of 2xy with respect to x is 2y. Because 2y is, we're treating this as 2y times the variable x, where y is a constant. That'll probably be the main reason I might use that notation. There's also another notation here that they put where they're using 1 and 2 instead of x and y. What that's essentially saying is differentiating it with respect to the first variable or the second variable. Normally, we don't see that very often unless you're in a higher dimensional case where you might be using variables where you actually have to number your variables because you just have too many of them. Instead of x and y or x, y, and z, you might have x1 through some big xn. And then you might, rather than having to write something like f sub x1 or f sub x2, you might just write that as f1. That's where I see that more often than not. Since we won't be going past three-dimensional stuff very often, we will see a few cases even in this section where we will go past three variables. But since we won't be seeing that very often or having to go too far with it, I'm going to just stick with using the actual variable name as our subscript. And then there's some people that like to put a big D instead of using the whole dx or ddy stuff. Probably won't be using that in this class, but there are some people that use that. Unfortunately, this is just one of those cases where a lot of people have various preferred notations. But if you stick with something like f sub x and f sub y, or even df dx, df dy, people will know what you mean by those. Really, the thing that's going to trip you up most is when you come across someone who's using a notation that you don't recognize. So that's why we have all these written out here. So hopefully that won't be too confusing. Do note here that we don't have to just be using x and y. We could use whatever variables we want to, and we just have to use those variables as your subscripts. So let's look at an example of that. So here we have a function, this time it's g, of two variables u and v instead of x and y. And they have this formula. We want to find the derivatives of this, the partial derivatives. So we will say g sub u. You could put g sub u of u comma v if you want. If you're not specifying uv, it's just kind of assumed here. We need to differentiate this thing. This time it's actually not it is a polynomial, but it's not expanded out, and we don't want to have to expand it out. But remember, when we're differentiating with respect to u, we're treating v as a constant. So this is a constant times u squared minus some other constant, all to the fifth power. And we just have to think of it that way and use the rules that we already know from Calc 1. We have some function of u inside a fifth power, and we want to differentiate it. We use the chain rule. So the outside function is the fifth power. We use the power rule for that. We bring down that 5. We have this, then we reduce the power by 1 to get 4, and on the inside of that, we still have what we have in here. So u squared v minus v to the third power. Now we need to differentiate the inside function, the u squared v minus v to the third power, and multiply it on the outside. The derivative of this, remember, v is a constant. So we have a constant times u squared. Derivative of u squared is 2u. And so we just end up with 2u times that same constant. Derivative of negative v cubed, well, v cubed is a constant. So we're treating that as a 0. Or in other words, if we go ahead and pull that and put out in front, because I feel like that looks a little nicer to do, we have 10uv times u squared v minus v cubed to the fourth power. Well, that's the derivative with respect to u. What about with respect to v? We do exactly the same kind of thing, except now we are going to treat u as our constant and v as our variable. That actually doesn't change this very first part of taking the derivative of the outside function, because we still have to use the chain rule here. We still have 5 times u squared v minus v cubed to the fourth power, but that is going to change what we have here. In fact, we could go ahead and write this out as the derivative with respect to v of this u squared v minus v cubed. Probably I should have written the respect to u up here like I'm doing here. Okay, so what's the derivative of this thing with respect to v? Well, keep in mind, u is being treated as a constant. And I'm going to keep saying that because you need to learn that. It needs to be driven right into your head that when we take partial derivatives, all we're doing is treating one of our variables as a constant. So the u squared is a constant. A constant times v, when we differentiate, we just get that constant. So we end up with a u squared. Minus v cubed, this time v is not a constant, it's what we're differentiating, and so we just differentiate how we normally would. So derivative of v cubed, we end up with a 3v squared. We're subtracting that. And this time, there's not really any simplification we can do. We just have two terms here. And so that would be our answer. So that's just the ways that we can go about doing that. Now in the next video, we're going to go through a couple other things that we kind of expanding upon our notation and what we can do with this, and talking about a particular theorem. But I don't want to cram everything into one video, so I'm going to go ahead and leave that for another video. So I'll see you then.